Hello everyone, welcome back to my channel. Today we're gonna discuss weekly contest 479. We're gonna discuss the first three problems of it. So yeah, let's go. This is the first problem: sort integers by binary reflection. So what this problem says is, you're given an integer array nums. The binary reflection of a positive integer is defined as the number obtained by reversing the order of its binary digits, ignoring any leading zeros, and interpreting the resulting binary number as a decimal. Sort the array in ascending order based on the binary reflection of each element. If two different numbers have the same binary reflection, the smaller original number should appear first. So this is the first example test case. Excuse me. So this is the first example test case 454. Okay, so I'm just gonna try to break this down for you. So this is 454. So the binary representation for 4 would be 100, 5 would be 101, and 4 would be 100. So what this problem says is, uh, when you reverse these binary digits, the number that you obtain, they are calling that binary reflection. So you need to sort this array based on their binary reflection. So this binary representation gets reversed, like this becomes 001, this becomes 101, and this becomes 001 again. So the problem says that we can remove any leading zeros, so we can remove these zeros, and now 4 is let's say mapped to 1 because its binary reflection is 1, right? This is just 1. 5 remains as it is, since 101 is a palindrome, so this will remain as it is. 5, I'm sorry, and 4 will again have its binary representation as 1. So we basically need to sort this array based on their binary reflection. So 1 will come, then this one would come, and then this 5 would come, so this will become 115, and then 1 maps to 4, 1 maps to 4, and then 5 maps to 5. So this would be our final answer, right? So this is the final answer, 4 for 5. So this is just basically an implementation problem. You can basically try to create a vector of pair. This is specifically for C++, not, this is not generic, but yeah, Java people must have something similar too. So I'm saying that we could have a pair of integers and store them in an array. So we'll map the binary reflection to the nums of I. So let's say my array is something like that, 6 and then maybe 8. So I'm just gonna write their corresponding binary reflection. 1 is 1, 2 becomes these are its binary representation, by the way, so we can just reverse them. So 1 0 becomes 0 1, this becomes 1, 101 remains as it is, so this is 5. 110 becomes 011, which is 3, this becomes 0001, which is 1. So I'm saying that we can map these values, these are binary reflection. Let me just use another color. So these are binary reflection, and then we can map them to their original form. So I could create a pair of 1 and 1. First there would be binary reflection followed by the number, the original number. So this is 1 and a 1, then there's 1 and a 2, then there's 5 and a 5, there's a 3 and a 6, and a 1 and a 8. Now we basically, these are the first ones are the binary reflection. So what we can basically do is just sort the array basically. Like we can use any STL or any collection of that native functionality, and then we can directly just sort the array, and then we can create another array containing these integers, right? So this will give us the sorted original form of the array. these are the original elements, right? The second ones. So we'll sort this array first by this um, first value, and then if at any point the first value becomes same, then we'll sort by second value. So this way we'll maintain the order. The only problem now is how we are gonna create this number that we get after reversing the digits. So this is pretty simple. First of all, what we can do is get its binary representation. So 5 binary representation is 101. So you know that we could get the binary representation by modding with 2 and then dividing by 2. So this is the representation of x, and this would be in a reverse format. So I can just reverse it again to if I have some number, let's say 12 1100. So when I try to obtain the digits, first I'll get a 0, so I'll add it here, then I get a 0, I'll add it here, then 1 and a 1. So this is basically the reverse format. So I'll just reverse it again, and now this becomes the correct number. After that I could form what I'm doing here. This was I was reversing that. Okay, yeah. So I might be doing this just for convenience. So after reversing this becomes something like this. So this is the binary reflection. So we need to now construct the final number, because we are dealing with arrays for now. We are storing the bits in an array, and now this will contribute to 2 to 0. This will contribute 2 to the 1. This will contribute 2 to the 2, and this will contribute 2 to the 3. So I could just multiply this 1 with 2 to the 0, multiply this 1 with 2 to the 1, multiply this 0. So these are 0, so this will remain 0. And then I could get my final answer like this: 1 into 2 to the 0 plus 1 into 2 to the 1, and then I could just add them, and then I'll get a 3, right? So this is basically it. So I'm saying that this will actually contribute 2 to the 0, or let's say 1 left shifted by 0 position. This will be shifted by 1, 1 would be shifted by 1, because this is 2 raised to 1, right? We can write that if 2 is raised to the 0, you could also use the power function, where you could raise this 2 to the power I, and so that is why we are reversing this this bits array, because when we get a 0 0 1 1 a 0 0 1 1, when we actually need this one only, but for our convenience we are reversing this, and now we know that this will contribute to 0 1 2 3. So we now can run a normal for loop, and then this will contribute 2 to the 0, 2 to the 1, 2 to the 2, and so on. So we could just multiply this 1 and 1 left shifted by 0, multiply this 1 by 1 left shifted by 1, right? Because 1 left shifted by I is equals to 2 to the I. That is what I'm saying. So this is equivalent to that. So we can create the number like this, and then we can just return this binary reflection. So this is basically the code. So I'm creating a new array of pairs. I'm pushing back this binary reflection with the original number. Then I'm just sorting this, and then I'm adding this the second value. This one, the second value. I'm just adding the second value to a new array, and then I'm returning this array, right? This is it. I hope you got it. Let's move to the next one. So this is the second problem. This was fairly easier than the first one, I would say, because a brute force solution would just work fine for this one. You just have to know sieve of error for this, calculating primes up to n. So yeah, I will do this. So basically this problem says is you're given an integer array integer n, return the largest prime number less than or equal to n that can be expressed as the sum of one or more consecutive prime numbers starting from 2. If no such number exists, then return 0. So return the largest prime number less than or equals to n. So we need to return the largest prime number that can be expressed as the sum of one or more consecutive prime numbers. So this problem says that we need to express the prime number as a consecutive. Let me write it down so that it would be easier. So this problem is saying we need to return the largest prime number which can be expressed as a sum of consecutive prime numbers starting from 2. So I'll just give you an example which would make it much more clearer. So let's say I have a 5 or n equals to 5. So you can you know that 5 can be represented as I'll just write the prime number. So 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime, 11 is a prime, 13 is a prime, 17 is a prime, 19 is a prime, right? And then 23 is also prime. So I've just written down some primes. So this problem says that we need to find the largest prime number that can be expressed as a sum of consecutive prime numbers starting from 2, right? So we need to the largest prime number that we find has to be lesser than or equals to this n, right? So we can see that 5 can be represented as a sum of prime numbers starting from 2, because 2 plus 3 is equal to 5, right? And 5 is a prime number. So if n equals to 5, our answer would be 5 itself. If let's say keep on adding these prime numbers, so 2 plus 3 is equals to 5. Now 5 plus 5 equals to 10, and then I add a 7 also. This becomes 17. So we can see that 17 is also a valid candidate for this one. So this is the problem basically says that we need to find the largest prime number, not only the largest prime number, but the largest prime number which can be expressed as the sum of consecutive prime numbers starting from 2. So we need to add all the prime numbers consecutively. So these are the consecutive prime numbers starting from 2. We have to add them until and unless we encounter a prime number, and then that could be our valid answer, but we need to maximize that number. So this is 17 is a valid candidate for this one, because 17 can be expressed as the sum of consecutive prime numbers starting from 2. So 2, 3, 5, 7. If let's say a 5 was missing, there was some number in which 5 was missing, then this will fail this will fail actually these requirements, and so this will not be a valid candidate for this particular answer, right? So have you got it? So now the problem is just reduced to playing with the primes. Whenever we encounter a problem related to primes, I would say use sieve of Eratosthenes. So we can just use a sieve of Eratosthenes to determine that if an number is prime or not. So you can see the constraints, they are from 1 to 5e5. So array of 5 could be from 1 to 5 into 10 to the power 5. So these are not very large constraints, and sieve of Eratosthenes actually takes order of n log n, right? So you can basically generate all the prime numbers in n log n time to determine in O1 if that particular number is a prime number or not, right? And then you can just basically run a basic brute force. You can start from 0. So let's say I have a for loop here. I can start from 2 and then I can go all the way up to n, and then I'll maintain a sum also. I'll check if the current number is prime. If the current number is prime, I'll add that to my sum, because I have to anyways add that to the sum, because the problem says a consecutive prime number starting from 2, right? So if it's consecutive and they start from 2, then if I encounter a prime number, then I will have to add that to my sum, right? So I add that number to my sum. Then I check here also if my sum has become a prime. So if my sum had become prime, then I can just update my maximum variable to contain this sum, and then I can loop over till n, and then I can just return the max, right? So this is probably it. We just had to run a brute force. So you can see the code. I ran a sieve of Eratosthenes here. This boolean computed variable is for avoiding recomputation for every test case. So I'm setting this true here, and so this remains true, and this this function do not run again and again. This will save us a lot of time. And then I'm having two variables over here, sum and max. If I encounter, I'll start my loop from 2 and go all the way up to n. If the current number is prime, then I'll have to add that to my sum. As soon as my sum becomes greater than max n would be 5 something, a little more than that. If my sum becomes more than that, or if my sum becomes more than n, I'll just break out of the loop, because now the answer is not possible, because we need to determine the particular answer that is at most n, right? So now if the sum has become a prime, I'll check that here. If my sum has become a prime, then I'll just update my maximum to contain this, to have this sum, and then I'll just return this maximum over here. And this is all. This was just a brute force solution, I'll say. The first one had a much more trickier implementation than this one, I would say. But yeah, this is it. Alright, okay, so I hope you got it. Let's move to the third problem of today's contest. So this one was actually trickier. I had to spend a little time to figure out the mathematical relation, but yeah, let's see. So the problem says you are given a positive integer HP and two positive one indexed integer arrays, damage and requirement. There is a dungeon with n trap rooms numbered from 1 to n. Entering room I reduces your health points by damage I. After that reduction, if your remaining health points are at least requirement of I, you earn 1 point for that room. Let score J be the number of points you get if you start with HP health points and enter the rooms J plus 1 to the all the way up to n in this order. Return the integer score 1 plus score 2 and up to score n. The sum of scores over all starting rooms. Yeah. They have also added a note here saying you cannot skip rooms. You can finish your journey even if your health points become non-positive. Okay. So what this problem says is we have been given a variable HP health points, right? And we have been given two arrays. First one is damage, and this is a requirement, second one. So the damage array will tell when you enter the room I, let's say. So let me just write it down. This is, let's say, D1, D2, D3 and all the way up to Dn. Similarly for requirement as well, I'll have a R1, R2 and all the way up to Rn, right? Now the problem says if you enter the room I, so I is equals to 2 in this case. If you enter a room I, then you'll deal a damage of di, and your health point will reduce by di, right? So if my HP was x, then my new HP would be x minus di, and if this new HP is greater than equals to requirement, then we can basically add a point to our answer, right? This is the basic problem statement. And now score of I, they have also added one term, which is score of I. So score of I basically is that how many points you can score when you, let's say, enter the room at the ith position. So I enter the room, not from the it is not always necessary to enter the room from the first room, from the first one itself, right? We can enter the room from any point or any room we want. So score of I will determine the starting point of the room would be I. So let's say I equals to 3 in this case, and this is the starting point. And now how many points can I earn if I begin with this point and then go all the way up to dn, right? So if I begin with d3, then my HP is, let's say, x. I'll do a x minus d3, and this is a permanent thing, right? So my new HP is HP equals to x minus d3. So this is my new HP. If this is strictly greater than equals to R3, right? So yeah, if the damage that I dealt and um, that damage reduces my HP by some points, and then still if my HP is greater than this R3, then I could add a +1 point to this and then move on to the next room, right? Similarly for next room as well, this will be my new HP x minus d3, and then I could do a x minus d3 and a minus d4, because this was the original new HP for me, and then I do a minus d4. So this is the new HP now, and then if this new HP is greater than equals to R4, then I'll add a +1 point to this one also, and similarly so on all the way up to n. So this is score of I. So we basically need to calculate all the score from 1 to and up to n, or in easy words, we need to calculate the total points that we earn when we begin from the first one, the first room, when we begin from the second room, when we begin from the third room, when we begin from the fourth room, and so on till we until we begin from the last room. We need to calculate this, right? The first thing first, let's say take this first sample so that it would be much more easier. So HP equals to 11, damage equals to okay, this is requirement. So damage is 367 and 425. This is the first room, the second room, and the third room. Okay, now basically the score 1 would be my initial HP is, I'm simulating the operation for the when I begin from the first room, score 1. So my initial HP is 11. I enter the first room, and now my HP is reduced by 3, which is 8. 8 is greater than equals to 4, so I'll add a +1 point to here. Now I get to the second room, then I deal a damage of -6, so my HP further reduces by 6, and then it becomes 2. 2 is greater than equals to requirement of 2, so I'll add a +1 here as well, and I'll move here, and then 2 minus 7 is -5, which is lesser than this, so we'll not add anything, and then we reach to the end of this this thing, and our score becomes 2 for this test case. Similarly, score of 2 would be the score when I begin from this particular room. So when initially my HP is 11, when I begin from the second room, it gets reduced by 6, so it becomes 5, right? This 5 is greater than equals to requirement of I, so I'll add a +1 here. Okay, now I move on to this one. Now my HP is reduced by 7, so this becomes -2, and -2 is actually lesser than this, so we'll not add anything here. So now this becomes 1. Now as for my score 3, I'll begin from this one, right? My HP initially is 11. This is HP is the initial HP for calculating every score. So if I'm calculating score 1, this would be my HP. Again, if I'm calculating score 2, this will get again 11. This will become again 11, and then I can perform operation. So this change is not permanent, right? Now if I begin from the third room, my HP gets reduced by 7, so this becomes 4, and 4 is strictly lesser than this, so we'll not add anything, and this will remain 0. So the sum of total is 2 plus 1 plus 0, which is 3. So 3 is our final answer. As you can see, 3 is our final answer here. So now question is how to do this. So first of all, I would advise you guys to think in the direction of prefix sums, because we don't have much to do in this problem, right? Let me just write that down. And HP was 11. So we don't have much for this this problem. Let's say we iterate on all the scores. So if I equals to 1, we need to begin from the first room and go all the way up to n. So if I am iterating on all the scores, so this is order of n already, right? So we cannot do a brute force approach and try going from here to here and calculate the simulate this operation, always decrease my HP and then check for every condition that if it is valid, if the condition holds or not, if HP minus this damage of I is greater than equals to requirement of I, right? So we cannot do this for every operation, because then it would become an n square approach. So we'll have to figure something else out. So I'm saying that if you guys think in the direction that if I'm iterating on all the scores from 1 to n, then we have to calculate the points that I gained in that particular, when I begin from that particular I, in order of log n or constant time, right? We need to do something like that. I'll repeat myself. If I'm iterating on all the possible starting rooms, then I'll have to calculate how many points can I earn when I begin from that particular starting room, right? In order of log n at max, or in order of 1. Okay. So I need to do something like that. If I can do something like that, then this problem would indeed be solved in n log n or n. But you'll see we cannot do anything like this, at least according to me. I think we cannot do anything like that, because how will you figure out how many points you can earn for any when I begin with any particular I? So if I say I begin with I equals to 2, and now how do you figure out how many points you can earn without actually simulating the operation? Because this can be very large. The requirements can be very large, so this is not monotonic. So for this you can have a 0 points, and then you can have 1 point for this, anything like that. This is not monotonic, that we'll get 1 point and then we'll get 0 point. Now this is for sure that this is not monotonic, so we'll need to figure out something else. We cannot just iterate on number of starting doors. If we cannot iterate on the number of starting rooms, then what else can we do? can we do something like, if I'm on this particular room, so this is I equals to 1 2 3, if I'm on this room, then can I do something like uh, how do I put it, that if I'm on second room, how many points this second room actually earns when I begin from 1 itself. So I'll take a bigger test case. This is I. So this, I'm basically saying, if I'm on I equals to 5, then I'm basically saying, can we figure out how many points that we can earn when I begin from 1, when I begin from 2, when I begin from 3, when I begin from 4, and when I begin from 5 itself? Can you figure that out? And can you figure that out, that will that be monotonic, that if going from here, that is starting from 1, if going from here to here, so I'm saying that if going from here to here does not I'm actually very sorry for the delay. I had some guest in my room, so I'm sorry for that. But yeah, let's continue. So I'm saying that if I'm on this fifth room, then if I begin, because if I'm on the fifth room, then this, if I start from seventh room, then I could not get any point from this fifth room, right? If I start from sixth, then I could not get any point from this fifth room, because I'm starting from sixth room, and I'll only go to my right side, right? So if I'm on my fifth room, then can I get a point if I start from uh, one, and then I go all the way up to wherever I wanna go? But can I get a point if I start from 1? Can I get a point when I start from 2? Can I get a point when I start from 3? And can I get a point when I start from 4? And then can I get a point when I start from 5? So this is basically a monotonic function, if you see carefully, because if I can get a point when I'm starting from 2, then I can also get a point when I start from 3, then I can also get a point when I start from 4, right? Because the sum only, if I start from 2, the sum is only greater, right? And this is actually greater, the sum of 2 3 4 5. When I start from 3, then sum reduces by a bit. When I start from 4, the sum further reduces by a bit. When I start from 5, the sum further reduces by a bit, right? So this basically tells us that if I can figure out the first point where from where we can get a point to our I, so this is I. So if we can figure out the first point itself from where we'll score a point, then all the points after that will also score a point, right? So we can just take this length, and then these will be the total amount of score, or then or the number of points that this particular I generates will be the total of this length, that is 4. So this creates a point, this creates a point, this gives a point, and this also gives a point. So this will be 4, this will give us 4 points, right? Similarly, if we do that for all the indices and sum them up, wouldn't you agree that we'll get all the points? Because if I'm doing this for 7 or 8, then I'm basically figuring out from when I start from 1, how if I can when I'm starting start from 4, then can I get a point? Then when I start from 2, can I get a point? When I start from 3, can I get a point? Can I get a point? Then when I start from 4, can I get a point? And let's say I get a point when I start from 4. So if I get a point when I start from 4, I'll also get a point when I start from 5. I'll also get a point when I start from 6. Because this sum, basically what we are doing, we're decreasing this sum of subarray from HP, right? we're actually subtracting the sum of subarray. Let's say if I'm subtracting the sum of subarray from 4 to 8, and this is actually greater than requirements of I, that is requirement of 8. So then this when I subtract the subarray sum of from 5 to 8, this will be somewhat lesser than the original one. So this the overall answer would be somewhat bigger. So this will anyways be true, right? Because 8 is constant. So if we can get a point from 4, we can also get a point from 5, from 6, from 7, and from 8 as well. So these are the length of this would be the number of points that we can score for this particular index, and this will be my answer. Now the thing is, how can we find this index? That will tell me that will actually give me how many points that I can score for this particular I. So basically we can write a relation. If you think carefully, we can just write a relation that something like let me use some other color. Okay, so I can use a relation. So I want you guys to think in the direction of prefix sum. So if this is prefix of r, wouldn't you agree that we will need to find a prefix of L? This is a prefix of L, so that p of r minus p of L will actually give me sum from here to here. So wouldn't you agree that we need to find the smallest possible or the earliest possible p of L, such that when I decrease that from PR, that is, for getting a subarray sum, we do a p of r minus p of L minus 1. So I'm not doing L minus 1, I'm just taking the L to the element 1 before it itself, right? So if this is p of r, and let's say all the elements from 5 after all the elements after 5 score a point. So I need to find I'll find where this condition becomes false for the last time. So 4 does not satisfy the condition, or when we start from 4, it does not give me a point, right? So it means that when I will start from 3, but then I will also not score a point, because the subarray is getting larger. The subarray is getting larger, right? When I start from 2, then also I will not get a point, right? Because this is also very larger. This is larger. This is larger, right? So I'll basically write the subarray sum would be this subarray sum from 5 to 8 would be given by p of r minus p of L, and then this is the subarray sum from 5 to 8, right? Subarray sum p of r minus p of L, and when I subtract that from HP, we are basically subtracting all of these from HP, right? If I enter from room 5 and go all the way up to 8, then I'll decrease a 5, then a 6, then a 7, then a 8 also. So this is basically I'm decreasing all the sum of this subarray, right? So I'm basically decreasing this sum of subarray from this HP, and this has to be greater than equals to what? Requirement of I. This has to be greater than equals to requirement of I. Simple, right? So when you open this expression, we get a HP minus P of R plus P of L greater than equals to requirement of I. Okay, now we can separate the variables, keep P of L at one place, and then transpose all the things to the right. So this becomes something like this, and this is our final expression. This is our final expression. So P of L is greater than requirement of I plus P of R. This is not requirement of I, but requirement of R itself, right? This is requirement of R. This is P of R, so the requirement will be requirement of R itself. So this is requirement of R. So P of L has to be greater than equals to requirement of R plus P of R minus HP. So I'll add P of R with requirement with its corresponding requirement, and then I'll subtract that from HP, and I'll subtract HP, and this says that P of L is actually greater than equals to this following expression. So I'll compute this expression, and then I'll just compute its lower bound, because this can be greater than equals to that. P of L can be greater than equals to this one. So I'll compute this expression, and then I'll just get a lower bound. So the lower bound will give me the index, this index, or I'm sorry, this index, and then I can just do a R minus L thing, and then I can add that to my final answer, right? This is essentially it. We're doing that. We're creating a prefix array, then we are forming the prefix array. We're creating a score. We're creating a score here. Then this is our expression, that prefix of I plus requirements of I minus HP. This is I plus 1, because I'm taking one based indexing for prefix sums, because 0 can also be a valid, this can also become negative, right? This can also get negative if HP is very large, then 0 will also be a valid answer. So that's why I'm creating a prefix sum of n plus 1 size, and then I'm also handling this case for 0. Then I found the lower bound for this particular thing. If this is greater than this particular I, so if I'm here, and then I get an index, let's say right to this particular point, then I cannot form a subarray, right? And so then I just do I minus idx plus 1. Then plus 1 is I'll just explain why I'm doing a plus 1 here. So if I write down the first example, first sample, this is HP was 11, damage, I'll just add a D for damage, and then 367, and requirement, I'll write a R for this, just 4 to 5. Let me take an example for this one. When I begin with I equals to 2, this is 1 2 3. In my code I'm anyways following 0 based indexing, so this is not this is not 1 2 3, this is essentially 0 1 2, right? This is 0 first and the second room. So if I'm on the first room, then I do a D plus R and then subtract that from HP. So 6 plus 2 is 8, right? And 8 minus 11 is 3. So I need to find the lower bound of 3. I'll also write a prefix sum here. So this was 0 for 0th index, then for 1 becomes 3, then it adds 6 to that, so 9, and then it adds 7 to it becomes 16, right? So we need to find the lower bound for this one, and the lower bound for this one is actually this. The lower bound for 3 is 3, and the indexing are 0 1 2 3. But you can see that this 3 is not for this first index or the first room, this 3 is for the 0th room, right? Because for prefix sum array we are calculating this one based indexing on the basis of one based indexing, right? So that is what I'm saying, that if I land on the first index in the prefix sum, that means that is the prefix sum for the I minus 1 index. So 3 I'm getting because of this 0, right? Not because of this first element. Because of this first element I'm getting a 9 here, because I'm adding a 6. So that is why I add a plus 1 to it, right? Because 1 minus 1 would be 0, but in this case this is valid. When I begin from here to here, this is valid. When I begin from this one itself, I'm sorry. So that's why I'm adding a 1 plus 1 to it, and then that's pretty much it. I'll just return my answer, and that is all. So that is all for today's contest. I hope you got to learn something today from me. If you liked my explanation, you could tell me that you understood the solutions. Otherwise you can also let me know if you didn't understood it. Anyways, thank you for watching. Stay tuned.